For years, the artificial intelligence industry focused on building massive, static brains through deep training. Today, the objective is to deploy those models as autonomous agents, software that can reason through multi-step problems and act in real time. Legacy GPU architectures were designed to ingest mountains of data simultaneously. But when an AI agent needs to pause, think step by step, and interact with the real world, that monolithic approach is too slow. The hardware cannot respond with the agility these systems require. A specific physical wall limits the industry, the decode bottleneck. Decode is the phase of processing where an AI actually generates its response, producing one single piece of information, or token, at a time. This slowdown is not a software error that can be patched. The delay is a result of how current silicon handles memory. Achieving real-time agents requires hardware that obeys a completely different set of physical rules. To understand why the silicon is failing, we have to look at how an AI speaks. Text generation is a sequential process. A model calculates the first word, and it must finish that specific calculation before it can begin determining the next one. High bandwidth memory, or HBM, was designed for this wide, multi-lane structure. It is perfect for moving massive datasets during training, but when an AI only needs to output one word at a time, that 1,000-lane highway funnels into a single sequential lane. Because the processor spends most of its time waiting for that single word to clear the narrow memory exit, the system becomes memory bandwidth bound. Raw computational power is irrelevant if the memory cannot feed the chip fast enough, causing the entire system to grind to a halt. Moving past this physical speed limit requires moving away from high-capacity memory. To achieve instant generation, the hardware must be engineered for pure velocity. In early 2026, NVIDIA spent $20 billion to license technology from Groq and hire its senior engineering team. They integrated Groq's specialized language processing units, chips built for high-speed text generation, into their new Vera Rubin platforms. The Groq LPU discards high-bandwidth memory entirely. Instead, it relies on static random access memory, or SRAM. SRAM stores data directly on the processor chip, removing physical distance. Integrated into the silicon, a single LPU pushes data at 150 terabytes per second, 7 times faster than standard GPU HBM4 memory. By placing both chips in the same data center rack, NVIDIA divided the physical labor. Rubin GPUs handle the understanding phase, reading through thousands of pages of context, then pass the baton to the Groq LPUs for the actual word-by-word decoding. This hardware fusion creates a specialized engine. It possesses the deep reasoning required for complex problems and the speed to interact with users without latency. The LPU maintains this velocity through a deterministic architecture. Instead of guessing where data should go on the fly, a software compiler pre-orchestrates the exact path every piece of data will take before the calculation begins. A single chip holds 500 megabytes. To scale up, NVIDIA networks 256 LPUs together inside a single LPX rack. They operate collectively, creating a 128 gigabyte pool of fused memory. In practice, this rack-scale determinism allows massive AI models with over 1 trillion parameters to generate hundreds of tokens per second for an individual user. The output flows faster than a human can read. Bypassing the decode bottleneck removes the physical barrier to real-time AI. The raw electrical power of the data center is converted directly into seamless, instantaneous conversation. As these systems become essential, nations are increasingly building sovereign AI, domestically owned compute clusters trained on national data rather than relying on centralized foreign clouds. To run public utilities, like an AI doctor or agricultural advisor, for millions of citizens simultaneously, the hardware must process requests locally and instantly. It requires rack-scale inference to function without the lag of distant servers. The most aggressive adopter of this model is India. Through a $1 billion government initiative, the nation is building its own computing ecosystem to host independent intelligence utilities. Indian data center providers are deploying tens of thousands of NVIDIA nodes to run domestic foundation models like ParitGen. These are designed to serve the country's population across dozens of regional languages. By owning the physical chips and localized data, these nations stop paying rent to foreign tech giants. They now use domestic hardware to manufacture their own native intelligence for local public services. Data center architecture has shifted toward a new model. These facilities function as intelligence factories, where raw data is converted into refined reasoning in real time. For 40 years, the internet ran on a search and retrieval model. You typed a query, and a server found an existing document. Now, the hardware synthesizes a bespoke answer on demand. This engineering breakthrough turns reasoning into a kinetic utility. Like the electrical grid, this infrastructure powers new sectors of the global economy. By re-engineering the memory pipeline to bypass the decode bottleneck, the integration of GPUs and LPUs has changed the technical baseline. Real-time agentic reasoning is now the standard requirement for global computing.